My translation might be a little bit different from yours, but literally, you should open this URL, and you should follow along with me, because I think our translations are really close. So, chapter 1, verse 3. Then God said, "Let there be transistors," and there were transistors. God separated base from collector and emitter, and God saw that the transistors were good. Then God said, "Let the transistors put forth PNP and NPN junctions, and compilers yielding machine code, and languages of every kind on the earth that bear logic with the seed in it." And it was so. Amen. And the earth brought forth fruit of every kind, with string copy, string cat, string compare, and sprintf. And God saw that his creation was without good or evil, white hat or black hat. And then God said, "Let us make many a Malroy in our image, according to our likeness, and let them have dominion over every creeping thing that creeps on the stack." That's really word for word of the Bible. Like 126, if you're following along. And so he did. God blessed them, and God said to them, "Be fruitful and multiply, fill the stack and sub it, and have dominion over all that executes upon it." And the Lord God caused a while loop to fall upon the Malroy, and they idled. And then he took one of their ribs and closed up in its place with bad food. And the rib that the Lord God had taken from Malroy he made into grep, and he brought it unto Malroy. And God said, "See, I have given thee grep, that you may go forth and enjoy all that I have created, that you may partake of string copy, string cat, string compare, sprintf, and know not of labor." And the earth was filled with Ode, and it was good. Amen. You can say amen. You know, it's like Sunday, the house of God. We can have a back and forth here. So, chapter 3, verse 1. Now the InfoSec industry was more crafty than any other wild animal that the Lord God had made. They said to the Malroy, "Let me tell you about something we have called 20% time." Many Malroy saw that InfoSec was good for food, and that it was a delight to the eyes, and that it was to be desired to make one wise. Then the eyes of many Malroy were opened, and those that partook were known as Alice and Bob. And in InfoSec name, they did create memory tainting and ASLR, and of course, we all know many other devices that have come. But what we have here is a moment in which sin was created. Before this moment, there was no such thing as white hat or black hat. In paradise, there weren't these definitions. There was no advanced persistent threat, and we lost paradise forever. But I've had a vision, and it's all the way back in verse 3. Then God said, "Let there be transistors," and there were transistors. And I'm here to tell you, brothers and sisters, there is a new paradise, and it's called hardware. So, right. Because basically, it kind of feels like, as I'm doing a lot of embedded analysis, that somehow this feels like the 90s that I remember, where you could just sort of grep across a bunch of code and find a bunch of string copies and like have some Ode. So there's a lot of progression, evolution still to happen in this phase before we are corrupted. So my talk is going to be about the techniques that I use. I don't know if you saw, there's a couple other talks here. Stephen Ridley gave a good talk, an excellent talk on his techniques and workflow, and some tools that I've created to sort of make my life a bit easier. So I'm just going to start with the tools, since that's the interesting stuff. Right. So I have a tool. These are Arduino based. Everyone can laugh. I don't care. That's what grep is about. You can laugh at it, but it's effective. So these are tools to sort of scan all the pins. When you open a device, you have all these pins in it, and you don't know which protocols are being spoken. If you can figure that out, you might be able to modify firmware, dump firmware, access the device, and the other talks gave some examples of this. So the problem is if you have a lot of pins, it can often be a suicidal endeavor to figure it out. Despite what my shirt looks like, I'm still living, and the reason why is because I make tools. So one of the tools is a serial scanner. It speaks serial in software, and it scans the different pins. These are the tools I'm going to go over. The other is a JTAG scanner. It speaks JTAG in software and scans all the pins. And then the other is a tool to dump memory. All this using really cheap hardware. So another thing that has happened before this whole lecture, we started preparing sort of a book It's not really a book, it's kind of like an exhibition, and I've been working with a photographer and an artist, and these are ceramic copies of electronic devices. They're not painted, they're real ceramic copies. And so on the left you have your Arduino. From the left to right you have a breadboard with some shift registers and a multimeter and our target. This is all you need to do most of what I'm about ready to talk about. So the concept in photography was by Hannah Foreman. And actually the sponsor, the company Recurdy Labs, is sponsoring a lot of the work to build and illustrate this stuff. So first we have our target, an example target. We have a CPU, and there's a bunch of various pins and pads and vias, which are through holes, that probably connect to UARTs, serial, JTAG, other interfaces on this, and we want to figure out what's on them. The first thing with these tools that you need to do is to sort of map the electrical characteristics. So for that, you need a multimeter, and you take the plus and minus probe while the device is on, and you sort of go from pin to pin to figure out what the voltage is. After that, you get a map that's kind of like this for a particular pad, and already with that information, you can start to deduce certain potential protocols that are being spoken there. For instance, with this, I would likely say there's not JTAG here, or not something that's very close to the CPU, unless the CPU's voltage is at 3.3 volts. If it's a low voltage CPU, then having a higher voltage here probably means it's not something very direct. It could be serial, since that's very common, but that's basically important to do to be sure you don't break your microelectronics. Right. So what you do is you basically load this sketch at that location onto your Arduino. You attach to all the pins. You want to be sure that your Arduino is working at the same voltage or near voltage of your target. You can buy Arduinos in all sorts of voltages, so just some of them are switchable. And so after you plug it up, you'll open a serial console, and the help menu will basically describe to you all the different tests. And I'm just going to walk through them real quick. They're really simple. So the first test is just a passive parallel scan. So it just sort of monitors the pins for X number of seconds or minutes and tells you if there was any activity. So down in the bottom there, you see these pin name definitions like pin 35, pin 27. Those are whatever names you set in the software. And it tells you when it toggles from a 0 to a 1. If you had some serial activity, you would expect a lot of activity on a particular pin. And so we don't really see that going on here. This only works if your target actually has a console or has some activity on boot. If your console does not have activity by default, and it's, let's say, waiting for a carriage return or waiting for some sort of wake-up signal, then a passive parallel scan, a logic analyzer, and an oscilloscope, none of those will really detect this. So what this tool does, the next test is an active parallel scan. In this case, it takes a bunch of wake-up signals that you've defined, such as a 0A for carriage return, and there's by default there's 3 different wake-up signals, but you can define your own. And then it tries at every possible baud rate to pick one pin as the TX pin, send the wake-up signal, and then it checks all the rest to see if there's activity. Here again, we don't really see much at 9600, and so then it tries 38, 400, still nothing, and then at 115200, we all of a sudden have a ton of activity on pin 27, so we can probably assume that that is the target's TX or RX. And actually, because this is active, we also know the pin that it sent was pin 33, so we actually already have the RX and TX in this scenario. So once you have that, basically you then plug up to some serial dongle of some sort, USB to serial, or your logic analyzer if you want, or whatever you have, and monitor the data or connect to the console or things like this. So that's the serial scanner. The other one is the JTAG scanner. I mean, you would basically run that for every pin set, and then you would decide, okay, I didn't find serial, now let's move on to JTAG. And so then here we do the same thing. We connect it to the device. We load a sketch. We connect the serial console. But maybe I should explain to you a bit about JTAG first. So JTAG, you're probably all familiar with serial. So JTAG is a very versatile interface for debugging all sorts of stuff on a device. So I don't know if you remember the Xbox red light and bug. where some chips sort of got desoldered a bit. So this is one thing that JTAG is meant to help check automatically. And here you have, I mean, if you didn't have JTAG, how you would have to check it is with X-ray, really expensive equipment. And so here you have, for instance, an image that shows you some solder joint that's just not very solid. So JTAG makes it easy to automate this. It's also used for checking connectivity between chips to be sure that, let's say, the traces on the PCB, the board, that they're also healthy. It's also used to check the state of pins on a chip, a JTAG-enabled chip, and some of the registers that are inside. So you can connect up to the JTAG port, query a large register, and get like 30, 40 bytes of data that each bit represents the current state of one of the pins. It's also used for on-chip debugging, which is probably what a lot of people here are familiar with. And this allows software developers to program memory and do like actual debugging with GDB or whatever other debugger you have. So because of its versatility, it's used at every layer of the development cycle. So it's used by ASIC designers, it's used by PCB designers, it's used by the embedded developers. So that because of that, it's kind of left around a lot, at least in the early revisions of devices. So you can almost always find it somewhere. And yeah. So a bit about what we're looking at. This kind of describes the registers and the pins of JTAG. So to go over them real quick, we have an input pin called TDI. We have an output pin called TDO. And then we have a clock pin, which is used to sort of toggle bits out of a register. And then we have the TMS pin, which sort of controls the state machine. It's the TMS pin and the instruction register that ultimately determine which set of data we're going to get on input and output of JTAG. So those are the 4 pins, and they're very important. The registers themselves, there's certain standard registers. There's a lot of other registers that could be vendor-specific, but there's very specific standard registers, and one of them is the ID code register. And this is a defined width of 32 bits, and it has a defined structure that defines the manufacturer and all this stuff. Another standard register is the boundary scan. That's the one that gives you the state of every pin that's on the device and some of the internal registers. And then we have the instruction register, which I described, and the bypass register. The purpose of the bypass register is so that you can chain them together. Several JTAG-enabled components on the same line, input and output line, and still be able to address them. I won't go into that in depth, but the important point here is my scan uses 2 registers to detect JTAG. Most standard JTAG devices will either have the bypass register by default on startup or the ID code register by default on startup. So if I try to detect a bypass register or detect an ID code across a certain set of pins, then with that I can determine if I have JTAG or not. So again, we take our Arduino, we load the sketch, we plug it up to one cluster of pins. We open a serial console. There's a lot of documentation in the code and the help that you get when you connect the serial console. But again, we're running these 2 basic scans, the ID code scan and the bypass scan. So the first scan we're running is the ID code. Again, we have these pin names that we've defined in software. And here it tries every possible combination. And at some point, we get down to the bottom, and we have an actual ID code of an LPC chip. The way the code actually works is if it gets an ID code that's not 0, all zeros are all ones, then it says, oh, I have an ID code. For a normal pattern scan through the bypass register, which is just a passive register that just shifts one bit in and one bit out, here we shift through this pattern. Again, it runs over every possible combination, and then in the end it says, oh, I found it here, and then it detects the instruction register length, which becomes important later for connecting to JTAG. Yeah, I guess I have that duplicated? Yeah. Okay, so let's assume that we didn't get access to JTAG. With JTAG, we would connect a JTAG controller, start doing debugging, check if we can access the memory, things like this. And the next step to get access to the firmware on this device would be to desocket the solder and sort of dump it. And you can buy all sorts of programmers for this. Some of them are very expensive. Some chips really don't release their data sheets to really write a programmer for it. And others actually have NDAs, and they're just very difficult to get a hold of. So this one costs $20, and you can dump parallel memory with it. So in this scenario, yeah, this is a more clear, accurate sketch of that. In this scenario, we need to desolder the chip out of the target and put it in what's called a breakout board, where it just resolders in and then it exposes all the pins on a larger pin set so that you can attach to it more easily. So to desolder the chip, I have a video online. You can see you can do this really easily at home with just a soldering iron. You add a bunch of solder to one side, and then you sort of take the solder across and you bridge all of the pins. And now this means when you apply heat to one point, all the solder will become liquefied, and then you can lift that side up. So yeah, this is a little tedious, but yeah, so basically that side's now mostly detached. And then you repeat and do the same thing on the other side. Yeah, and once you have it off, you just basically need to clean the pins using solder wick, and then you can reattach it into your breakout board. So another way to desolder, if you don't have a soldering iron, is to use a candle if you don't care about your target. So in this scenario, I'm using a candle on a processor, but we're desoldering. It's the same technique. Right. So the candle's underneath the board, and the processor's on top. And then you just leave it there for a while, and put a little bit of pressure, and then eventually it pops up. Right. Yeah, so once you have the chip, you put it in your breakout board. The reason that we need the shift registers in this breadboard, which I'm about ready to show, is because there's a lot of address pins on a chip. You might have like 16, 24, however many address pins, and then a bunch of data pins for parallel access to memory. So the Arduino, for instance, only has 14 input and output. So somehow we need to multiplex our output and our input. And to do that, we use shift registers. So in this scenario, basically, you take a bunch of shift registers that allow you to send one byte into one pin. It uses one pin on the chip. You send a whole byte in, and then you toggle another pin, a state pin, and then it puts that byte out on 8 other pins. So using one pin from your microcontroller, you can get 8 pins of output. And so basically what you see here in the middle is the shift registers that would basically allow for 24-bit address using one input-output pin of the Arduino, or 3 actually, but anyway. And so then you connect that to all of the address pins of your breakout board for your memory, and then that covers basically the address. All of these sketches, by the way, are made with fritzing, and they're very good for debugging while you're plugging all this stuff up, and those are available in the GitHub repository. The next thing is to do the same for data, because in this particular target, I had a 16-bit bus for data on the chip. And so there you use shift registers that allow you to accept 8 bits in and then shifts the byte, one whole byte out across one pin. So that's this scenario. And so then once you're done, you load the code onto the Arduino. You need to define certain things such as the input-output pins for your address and data lines. But you also need to look in a data sheet. This is the information you need. It looks complicated. It's really not. All you need to know is when one line goes high versus another line going low, and the specific order of them, because you can dump memory as slow as you want. So in this case, it's pretty standard for most chips. The code is already built for what you see here, and but you might check with your target memory to see if it differs slightly. And then you run the code. And the code just spits out the data. It asks for address 0, spits out the data across serial. Asks for address 2, spits out the data. And it keeps going on like that until you've defined it to stop. So in this case, I just basically run a serial terminal. And here I've turned logging on. I'm not sure if you can really see it. Yeah. So then I've turned logging on, and then I can just basically monitor that log file to see when it's finished. And I piped it into a hex editor. So it takes a long time. So normally I put like 2 LEDs on the address breadboard where the shift registers are so that I can see when the lowest bit is being toggled and when the last bit of the address range that I want is toggled, and once I see that the LEDs aren't moving anymore, that's another indicator to me that it's done. Yeah, it takes about 32 hours to dump 128 meg, but I don't care. I'm sure it can be optimized, and by all means take the code and make your own repository and do whatever you want. So that's basically the tools. That's really the meat of this. But Stephen really sort of went over his workflow, which I found was really useful. When you're wanting to get into hardware, the basic thing you need to have is how do you go about opening this target and what are the different steps that you should take in the progression of it. And everybody has some slight differences here, so it's nice to see how different people do this. But first, I don't know what type of audience we have, but I'll explain why we do this type of stuff or why you might do this type of stuff. So all of the open router projects depend on a community that takes routers that come, new routers that come to the market and sort of does exactly this. Analyzes them, opens them up, dumps the firmware, then of course you guys reverse engineer it, and then we port some drivers or figure them out and port Linux to it. And that allows for all sorts of creative projects, such as the Pirate Box, which is a file-sharing Wi-Fi point of presence like you have at the hotel. You can take this box into any cafe, set it up, and then everyone that comes in and accesses it can sort of share files and stuff like that. Of course, there's the Tor router, which allows for a transparent proxy in your home so that you can allow your neighbors or people in the street to use your wireless, but it routes everything over Tor, so you never get kickback from anyone if they're doing something like downloading files. So these depend on people like you and us opening hardware. Of course, there's other examples that you know about, like the Xbox. I really like the example of the original Xbox because if you go back to the original Xbox, we didn't have a home media center on our game consoles. And that, at least I first learned about it with the Xbox when it was hacked. The community came along and they created this whole idea of having a home media center on your game console. And of course now the 360 has that, the PlayStation has that, everyone has it. And for me, somehow it seems that actually these barriers that are set up to sort of prevent such a community developing almost creates the creative energy required to come up with really interesting ideas. On the other hand, that's really twisted because in Paradise, we actually had open devices. So yeah. So we wouldn't have had that problem. And of course, the Wii console, the Boot Me from all those guys from Team Twizzlers is the same concept. But I like to point out some artistic reuse examples. So at a school that I studied at in Potsdam in Germany, it was a design school, and they required all of the students to hack a keyboard in the first week. And probably 80% of these people came with little to no technical expertise. Why doesn't the video start? Oh, it does. Yeah, so they came with very little technical expertise, and they had to take apart a keyboard and make some sort of interface. And they came up with all sorts of interesting things in 1 week. And she made some game with some pressure sensors, and this guy made some glove with as a Guitar Hero interface just out of a keyboard. So our schools are interaction design schools and design schools, especially industrial design schools, they're very much getting more and more into reusing devices in some sort of creative way. And so I find it to be an interesting place to apply my skills. So you can apply it for security. I also do that as a consultant, but sometimes others here might find interesting application in art. One project that I got to do that was very interesting was with David Bortz from the Bezalel Academy of Arts in Jerusalem. He wanted to take some smart memory, shape memory alloy, and he wanted it to fluctuate at your heart rate. And shape memory alloy, I won't get into describing what it is, but it's a very versatile material. And so to do this, he needed to get a biometric monitor of some sort. And we started looking at schematics to build it, but we couldn't really source components easily in Israel at that time. This was like 5 or 6 years ago. So we just took a consumer device off the market, and then we opened it up and we started probing around, looking for different protocols, and eventually trying to find where we could get the pulse rate. Of course, for us this was easy. We had our pulse and we could take it off and on, and we would see what data we would get out of different pins. And so you might find interesting stuff and artistic reuse to apply your skills. So that's what we do it for. As far as my workflow goes, in my workflow, most of the times what I'm looking for is the human element. I mean, you can learn all the technical details and things like this, but ultimately it's the abstraction between the different types of developers, these ASIC designers versus PCB designers, they come out, that abstraction layer, that demarcation point often comes out aesthetically when you look at the device. So the way that certain things are arranged or that certain markings are there come out and they expose some of the logic of the developers, which can give you clues for reverse engineering or getting full access to the device. Now, one example I like, and it's very relevant for security, is here we have a smart chip under a bunch of epoxy. Epoxy is meant to be hard to remove. Of course, you can remove it with some heat and whatnot, but it should be hard to remove, and it's there to prevent someone from taking an oscilloscope or some sort of probe and attaching to the pins and manipulating that chip. So there must be some sort of security specification that says, okay, manufacturer, when you manufacture this, we require for our security requirements that you put some epoxy on this chip because it's very important to us. But this particular specification didn't get to the PCB developers because on the bottom, all of the vias, which are the through holes, are exposed. And for certain, those vias are for that chip. And so this type of abstraction between these really discrete different fields of development, and often they're completely different companies. The person making the PCB might not even be related to the company that's doing the software development, to the company that's making the ASIC, of course, et cetera. So it's hard for the security requirements to transverse all those layers. So looking for this human element is ultimately what I try to always keep in my mind when I'm going through my workflow. So how do I begin? Normally I take a photo of my target. So here we have just a common router. I take a photo of the front, I take a photo of the back, then I open them in GIMP and I align them nicely. And this gives me the ability to sort of see the front traces, that is the lines on the PCB, and the back traces together, which gives me all sorts of clues. So already with this particular target, we can see some, interesting things that we already want to look at, interesting pins or vias. So here we have some sort of set of, I think it's like 20, I don't know however many pads. We have 5 pads up here on the edge, and it's interesting, why are they on the edge? And we have these 4 vias in the middle, and 4 is pretty nice. I see that, especially on routers a lot, that's serial most of the time. So you could, at this point, even with that information, just start going after low-hanging fruit. You know, pull out your logic analyzer, pull out your oscilloscope, whatever, and start looking at this stuff. But with this particular target, I went a little bit deeper, and I noticed when I looked on the back side, you have all these pads. That is the little gold or copper pads on the back. And the thing that I noticed is that 4 of them have solder on them already. And so why is there solder on these 4 already? I'm sure there could be many reasons, and I would love it if someone came up to me afterwards and would give me a long 30-minute spiel on how this could be used. I'm sure I don't know. But I always assume if I see something like that these are interesting. So I decided to try to figure out what they were. So here we have both layers again on top of each other. And we have we have one processor up at the top, right, and that's a Texas Instrument. And that particular processor has all its pins underneath. So normally if I was to try to figure out what these soldered pads are, I would take out a multimeter and put it in beep mode, which is when you put the 2 probes together, it goes beep. And then I would try to connect one to the soldered pad and then try to go across and rake across the CPU or something and see when it beeps to know which pin it is. I can't do that with the CPU because all the pins are underneath. Of course, I could desocket it like you saw in the video before with a candle or whatever. But we have another one here. I'm assuming because those 4 have solder that they must relate to each other even. So we have another JTAG, this was JTAG and in, sorry, I gave the secret. But we have another microcontroller here, which is actually an FPGA, which is close to one of the pads. So I took the footprint from the data sheet that I could find online, because Xilinx gives a lot of their data sheets out. And I sort of put this around the image that I have here so that I could see what pin was what. And then I looked at the traces. I guess it's really dark here, but I'm not sure if you can really see these traces. But then just visually, I could look at the traces and sort of follow them, and I saw that these, from the footprint, the JTAG pins, there's the 3 on the top left, which is TDO, TCK, TMS, and then there's one all the way on the right, which is TDI. So I could see that the 3 on the left went to these resistors, and then went out and went into some vias, and then those probably went somewhere, burrowed into the board and went out somewhere. So based on that, I already found that one of those, and that pad with the solder connected to it, so I found that one of those was the JTAG of the Xilinx. And it's interesting because the other 3, which are near the Texas Instruments, there's no problem with them being spread out because you can chain together JTAG components so that the input comes into one chip and the output is on the other. So that's exactly what happened here. And then also in the end, I found that these 3 actually, with a multimeter just checking the continuity, check the beep mode, I found that those 4 all connect out to this particular missing connector, which means, okay, they could just attach a connector and then have access to JTAG. So looking at these elements like solder on pads, indentations on pads, which might be used for bed of nails testing during manufacturing, like a little needle indentation, these elements can kind of give you some clues as to what's going on. So yeah, just looking for that stuff, including like markings. So what markings are around in different areas for missing connectors, all this stuff can give you some clues. For example, in this particular target, I desoldered the flash, and then underneath I saw this, the outline there, and a new pads. All of a sudden I had these new pads, and I was very curious, what are these? And so I think I sent an email to Travis Goodspeed, maybe, and TMB Inc., Fieldstone Kane, a bunch of other people. I was like, what the hell is this? And they explained, oh, that's just for a socket, for a flash programmer socket, for standard CFI flash. So all of a sudden I was trying to figure out what this flash was for, and this particular pattern told me, oh, it's CFI. That's a common standard. I can buy the socket and just dump it. So looking at this stuff can help, because you're never always going to have complete documentation. So after looking at that stuff, I normally map electrical characteristics of these pins, again, to give me some clues. Here we see on the 4 pins that we thought was serial, we see 0 volt ground, 3.3 volts, and that's pretty common of serial. On the pads, we have all sorts of different connections. But the interesting thing I wanted to point out here is that the low voltage stuff. If your processor's running at a low voltage, and you find a bunch of pads that are also low voltage, that makes them closer to the processor. They're closer to it. They're not going through some voltage shifter or something. And JTAG almost always is at the voltage of the JTAG-enabled chip. So it's always at VCC. So the fact that these are at 1.8 volt, which is the VCC of the target chip, also gives us another clue that this might be JTAG. Of course, it could be a whole bunch of other things, but yeah. The other thing you might do is to actually not just check voltage, but check resistance, like to ground or to VCC of a processor. Because with JTAG, if we go back to this, we see these little symbols here, these whatever pumps. Those are actually called pull-up resistors. In JTAG, each of the lines should have a certain default state, meaning it should be at a 0 by default unless when there's no data, or a 1. So in this particular scenario, you can see that 2 of the required pins and 3 of the common pins should always be at a default state of 1, and they should have a pull-up resistor. And if you go and look at the specification from IEEE for JTAG, you'll see that they give a range of 1 to 10K resistor. So you can start looking around for resistance measurements that are within that range. But when they gave a schematic in the specification with like a common implementation, and they used 4.7K in that implementation. And probably on 50% of the targets that I come in contact with, they're using 4.7K. So automatically, 4.7K kind of gives me some clues. Of course, I'm desperate. When I don't have documentation, I get very desperate on these types of things. So yeah, so you can map resistance, and that might also help. After I've done mapping these things, I might again go after low-hanging fruit. And that is like just plug things up, plug up my logic analyzer, plug up an oscilloscope, start to try to figure out what it is by hand before I start to solder up complicated connectors to do scanning. What can help is to get data sheets, which is sometimes very complicated. But thank God for the Japanese and Chinese, because often you'll find like data sheets in Japanese and Chinese that you won't find in English. And of course, the websites that you're going to search for data sheets that are hard to get are going to be Pudin and Baidu and places like this, where you can find some data sheets. So this was like a data sheet. I was looking at a target, and I could not find a data sheet for it. So what I did was I took the number of pins, X and Y that I knew around, and then I started looking for other data sheets in the same family, like the same company that made this chip. And then I found one in Japanese that had the exact same footprint, and that gave me JTAG in the end. It told me where JTAG was. So being creative with data sheet hunting is very important. Or just having really good friends or really good connections to a black market or social engineering or something like that. So once you have that all mapped, you might, again, go use the tools that I said and scan it, attack it, and dump it. If you fail, you have to go back and take a closer look. You're going to fail because actually, well, I always fail a lot of times because at least on my, for my professional work, I often have time restraints, so I can't really, excuse me, spend a lot of time going over every possible combination and doing it in a linear fashion. I have to sort of make a broad stroke, then come back and make another one. So you are always going to wind up going back and trying to go over this again and take a closer look, for instance, looking for the different human elements, and just taking a closer look at the pins. And I mean, I've gotten as desperate as like mapping the resistance of every single resistor on a board. And yeah, so that's really pretty much it. There's a lot of research that can be done in this field. Like I said, I feel like my tools are like grep. I don't really think they're any more complicated than that. And I don't consider myself a good electrical engineer at all. And yet somehow a couple of people have respect for me. And I don't know why that is at all. Because really, I just do really stupid stuff. I feel it's really simple. And that's why I'm trying to write these tools in Arduino and other things like this so that everyone else can get involved and do it, because it's just a hell of a lot of fun. I mean, even just going over the slides, you could think of different things, so of research that you could do or innovations that could happen. So for instance, I run a scanning tool that sends a wake-up signal over serial, because normally if you don't want someone to find your serial console, well then be sure it doesn't print out anything, right? And then require the person when they connect to put in a carriage return, and then give them the login prompt. So you could imagine, for instance, now my tool makes that useless, but someone here could innovate serial port knocking. I don't know. And then you have to have a special pattern of wake-up signals. I don't know. So there's lots of interesting things that can be done on the defensive side. There's also things to do on the analysis or offensive side. So one of the things we started trying to do, we haven't gotten very far, is auto-tracing PCBs. That is taking pictures of the top and the bottom and then also shipping off the PCB to China. You can pay $90 and have every layer photographed for you. And then sort of doing auto-analysis of that to figure out where the traces go. That's one thing. Another thing is thermal imaging. I talked about this at the CCC last year, and then Star Simpson, she actually went and tried it a few months ago and did a lot of research on this, and trying to use a thermal imaging camera on a board and then applying heat to a line, and then perhaps you could see the trace within the board. Okay, yeah, I also thought it was awesome. But she did a bunch of research, and she found that basically the material of PCBs distribute heat really, really well, so you don't really get a clear picture. But she has a whole discussion on this. She just posted this a few days ago, her research on this. She has a whole discussion there, and there might be some avenues to improve that, for instance. Another thing that I thought, going back to the idea of data sheets, like finding this one data sheet that's from the same company, that has the same number of pins, but it's not the same chip, but it matches, and it's in Japanese. So it would be nice to have a database of all of the footprints from public data sheets, and then you could just sort of go to your target and say, oh, I have this many pins, this is the arrangement, tell me what data sheets that you have in any language for this. that would be very useful because right now that's just tedious work. And that's pretty much it, and there's all sorts of other research going on. So I'd like to thank Hannah Foreman, who did the photography and all of this amazing work with the ceramics, FX and Dirk at Recurdy Labs for sponsoring some of this stuff, Christopher Tarnowski at Fly Logic, Travis Goodspeed, Bushing Bunny, and all of the elders of the Church of Malroy that have helped me. And that's it. Any questions? Anyone want to repent? What? Oh, yeah. You can come take communion. Ushers, please pass out the tithing bucket, whatever.